Most textbooks assert that light travels at different speeds in various mediums. The higher the refractive index of the medium, the slower the speed of light. But does light genuinely slow down? If it does, how does it happen? There are numerous theories attempting to explain this phenomenon, many of which are flawed. So, what's the correct explanation? Is there even an absolute one? First, let's appreciate how challenging it is to alter the speed of light. For starters, the special theory of relativity is based on the invariant speed of light. Assume a train is traveling at half the speed of light. Light's speed remains constant at 300,000 kilometers per second. Secondly, by only modifying the energy of light, its frequency and wavelength change, but its speed remains the same. Lastly, photons, having zero mass, always travel at a speed of 300,000 kilometers per second. Other particles with mass can't achieve this speed. Accepting that photons slow down would mean acknowledging that they somehow gain mass when passing through a medium. Is that plausible? All these observations indicate that it's extremely difficult, if not impossible, to alter the speed of light. As early as 1851, Fizeau demonstrated using an interferometer that light slows down when it passes through a medium. However, slowing down could mean three things: a reduction in speed, an increase in distance, or an increase in time. The first interpretation, reduced speed, is similar to how humans walk slower in water. This slowing is due to the water's resistance, causing energy loss. As light loses kinetic energy, its speed decreases. This seems logical, but there are three issues. Does light experience resistance? Setting aside whether the concept of resistance applies to light. If it did face resistance, light would continuously decelerate in the same medium until it stops. Even if light did encounter some unique resistance, why would it continue at its original speed upon exiting the medium? How would light recover the lost energy? Assuming light can regain energy, why would changes in light's energy alter its speed rather than its frequency or wavelength? Some might argue that a denser medium has a higher refractive index, thus a slower speed of light. This is a valid point for the same medium. However, if you compare to different mediums, you'll spot the flaw in this argument. In conclusion, while various theories abound, understanding the nuances of how light behaves in different mediums remains an intriguing subject for physicists. The second theory suggests that, as distance increases, light scatters among the atoms within a medium, leading to a longer actual path, making it appear as though the speed of light has decreased. At first glance, this seems reasonable, but there are two issues with this explanation. First, light scatters in multiple directions. This would mean that after refraction, the light should spread out instead of converging, which contradicts actual observations. Second, each light path varies in length, leading to varying light speeds, hence this explanation is also incorrect. However, the phenomenon of light scattering does exist. For example, when you can't see a laser in the air, but can see it in water, it's because part of the laser scatters in the water, allowing some of it to reach your eyes. Yet, scattering cannot explain why light slows down in a medium. The third theory posits that as time increases, photons are absorbed and re-emitted by atoms. Since this process isn't instantaneous and there's a slight delay, it seems like the speed of light has decreased, even though its speed remains at 300,000 kilometers per second. While this seems plausible, and electrons can indeed remain in an excited state for a short period, there are two issues. First, quantum jumps are random and probabilistic. No one can guarantee that the re-emitted photon will have the same direction or experience the same delay. This is a fundamental characteristic of quantum mechanics. The same initial conditions can yield different results. Second, although the phenomenon of dispersion has proven that the frequency of light affects its refractive index, according to Bohr's atomic model, atoms can only absorb light of specific wavelengths. For instance, if a medium could only absorb blue light, theoretically, only blue light would slow down with a refractive index greater than 1, while other colors would remain unaffected with a refractive index close to 1. Thus, this theory is also flawed. Interestingly, the higher the frequency of an electromagnetic wave, The higher its refractive index and the slower its propagation speed. It's puzzling why high-energy electromagnetic waves travel slower through a medium than lower-energy ones. Let's leave that as a teaser for now, and we'll delve into the mechanism shortly. If all the above theories are wrong, what's the correct explanation? Is there a physical model that can elucidate this phenomenon? We know that according to Maxwell's theory of electromagnetic waves, oscillating charged particles can produce electromagnetic waves, and the frequency of oscillation matches that of the wave. When we say an electromagnetic wave has a frequency of 100 Hz, we're also indicating the oscillation frequency of the electric field and charge is 100 Hz. If oscillating charged particles can generate electromagnetic waves, can electromagnetic waves induce charged particles to oscillate in return? Electromagnetic waves have varying electric fields, so in theory, they can cause charged particles to oscillate. Is there evidence supporting this? Yes, antennas used in communication work on this principle. Transmitting antennas use alternating current to produce electromagnetic waves, whereas receiving antennas capture electromagnetic waves, generating an alternating current that is then converted into readable information. Interestingly, if electromagnetic waves can induce electrons to oscillate, can these oscillating electrons produce electromagnetic waves again? They can. This is why there are distinct designs for transmitting and receiving antennas, to minimize the ray emission of electromagnetic waves by the receiving antenna. Returning to the main topic, since light is an electromagnetic wave, it can cause electrons in the atoms of a medium to oscillate. These oscillating electrons then ray-emit light of the same frequency, entering a cycle. Thus, we get to levels or kinds of light. The first is the light emitted by the source, and the second is light emitted by the electrons. Compared to the first level of light, the second has a slight delay. When combined using the principle of wave superposition, we still perceive the delayed light. Additionally, the Langevin waves detected in 1920 directly demonstrated that electrons can oscillate like a spring and produce electromagnetic waves. From this, we can infer that due to the restorative force between electrons and atomic nuclei, they can engage in simple harmonic motion. Next, we need to prove that the electron and atomic nucleus form a damped oscillation system. Do electrons face any resistance? This is quite straightforward. An oscillating electron can radiate electromagnetic waves, implying it experiences energy loss. This resistance is also known as radiation damping. Without a doubt, the electron and atomic nucleus form a damped oscillation system. Furthermore, we must show that the electron and atomic nucleus constitute a driven oscillation system. This is even simpler. The oscillating electric field provided by the primary light serves to drive the electron's oscillation, indicating that the electrons and atomic nuclei in the medium are subject to driven oscillation. An additional point is the concept of natural frequency. For instance, if you observe a pendulum that oscillates 3 times within a second, regardless of its starting position, its natural frequency is 3 Hz. The natural frequency of the pendulum depends on its length and the gravitational acceleration, just as the natural frequency of harmonic motion depends on the mass of the object and the rigidity of the spring. Similarly, the natural frequency of electrons is expected to be related to their mass. Entering the final part, we'll demonstrate mathematically that there is a phase difference between the primary and secondary light, indicating that the secondary light experiences a delay. To prove this, we merely need to compare the driving force with the position of the electron. If there's no phase delay, theoretically, when the driving force or electric field force is at its peak, the electron's displacement from its equilibrium position should also be maximum. Using Newton's second law, we can determine the position of the electron. Various methods, like Fourier transforms, Laplace transforms, and convolutions, can be used to solve this differential equation. We find that the secondary light emitted due to electron radiation is slightly out of phase with the primary light, creating a phase delay of less than 90 degrees. With a vast number of atoms in the medium, the cumulative phase delay is significant. Not only do the primary and secondary lights superimpose, but other light waves also superimpose on them, causing further phase delays of less than 90 degrees. As a result, light passing through a medium experiences a total phase delay of less than 180 degrees. Recall the double-slit interference from high school physics, where light can produce darkness. Isn't that a violation of energy conservation? Not really. The energy merely gets redistributed. Similarly, light interferes in a medium, canceling out initial wave peaks. This phenomenon makes light seem slower in a medium. Even though both light and the electromagnetic waves emitted by electrons travel at 300,000 kilometers per hour, electrons radiate electromagnetic waves in all directions, interfering with other waves, further scattering the light and making its speed appear reduced. This explains the dispersion phenomenon. Why higher energy electromagnetic waves slow down more than lower energy waves in a medium? The oscillation frequency of high-energy electromagnetic waves is too high for electrons to keep up, resulting in more significant delays. This relationship between the refractive index of a medium and the frequency of electromagnetic waves is why quantum mechanics offers its own set of theories. Although various interpretations of this model exist, they are more or less similar.